Chapter 18 Notes. Let's start with a little review. Series circuits have one path for the electrons. It is one loop around. And the three things we have to have memorized about a series circuit: the current is the same for the entire circuit. The current that goes through the battery is the same current that goes through each one of the components. The voltage across each component is different. The battery is creating the voltage, and each one of the components is using a little bit of the voltage. You can see in this case it's a 2-to-1 ratio, so this resistor is using twice the voltage that this one is using. The resistances just add together, so 5 and 10 is 15 ohms for our net resistance. A parallel circuit branches into more than one path for the current. Proper way to draw a parallel circuit is nothing on top, nothing on bottom, and everything is on a vertical line in between the top and bottom. The current is different for each one of these vertical lines. The battery has a current, this resistor has a different current, this resistor has a different current. The voltage is the same for each component from top to bottom. If the parallel circuit is drawn correctly with nothing on top, nothing on bottom, top to bottom, the voltage drop across each one is exactly the same. These resistors add by inverse, so we would have 1 over 10 plus 1 over 5 makes 3/10 or 1 over 3.3. Going on with our notes, internal resistance. Batteries not only have a voltage source, but they have an internal resistance. It's usually very small compared to the resistance of the circuit, so it's often ignored. But today we're going to look at how that works. So these are drawings of a car battery. The posts that stick out of the battery are called terminals, and between the terminals we have an EMF, that's your voltage source. In this case, for a battery, it's a chemical reaction, and we have an internal resistance. When the battery is not hooked up to the circuit, or when the circuit is switched off, the voltage between A and B is called the terminal voltage, is equal to the EMF of the battery. However, when you hook it up in a circuit, when the current starts flowing, each one of the components uses a little bit of the voltage. So the terminal voltage from A to B is a little bit less than 12 volts. EMF stands for electromotive force. It is a source of potential difference. It's not a force. This is a question that will come up on a multiple choice somewhere where they're asking about electromotive force, and they'll ask you maybe about the units of it or something. It's not a force, it's not newtons, it's a potential difference, it's volts. The EMF is the voltage of the battery. All right, let's make a little note on here. The EMF is the voltage, the terminal voltage from A to B when there's no current flowing. When the current flows, we lose a little bit of our 12 volts to the internal resistance. Kirchhoffs rules. I've heard this name pronounced a bunch of different ways. My teacher at school called it Kirchhoff. I've heard Kirchhoff, I've heard Kirchhoff, so I looked it up.
Kirchhoff. Kirchhoff.
Kirchhoff. Kirchhoff.
Kirchhoff.
I think I'll stick with Kirchhoff. All right, his junction rule says, at any junction, the sum of the currents leaving must equal the sum of the currents entering. Now, the junction rule is only for a parallel circuit. At this junction up here, we have a current coming from the battery, and it splits into two smaller currents. The current from the battery is usually labeled I1, so we'll label the other two I2 and I3. The junction rule says that this I1 has to equal the sum of I2 plus I3. To me, that's just common sense. If I follow these currents over here, I3 and I2 meet up again at another junction, and they make this current on this side, which is current 1. So at this junction, we have I2 plus I3 equals I1. You can see mathematically these are the same equation. So normally when we're using the junction rule, we only use one junction because the other junction is exactly the same equation. The junction rule is a statement of conservation of charge. We have a certain number of charges or a certain number of particles coming into the junction. We need the same number of particles leaving. Otherwise, you're creating matter, and that's not possible. The loop rule says the sum of the change in potential around the closed path of a circuit must be 0. When you're going across a battery, you're adding voltage. When you're going across a resistor, you're losing voltage. So here's a series circuit. The loop rule works with series or parallel. And if I do a loop around this, as I go across the 12-volt battery, I'm gaining volts here, but I'm losing a little bit of voltage from this light bulb. I'm losing some voltage from this light bulb. I'm losing some voltage from this light bulb. So if I write it all out, I have 12 volts and minus a voltage for each of the light bulbs. Now I know voltage V equals I times R, so I can substitute IR for each one of those V's. So this would be the statement of the loop rule for this loop. Sometimes you can simplify these. These all have the same current, so I can factor out the I. Or sometimes you would divide through by I and get 12 over I equals RA plus RB plus RC. The loop rule is a form of conservation of energy. The energy that is made by the battery is the same energy that's used by each of the light bulbs. For a circuit, when we're talking about using energy, we're talking about the power. The power of the battery equals the power of each of the light bulbs added up together. That's conservation of energy. All right, let's look at some examples here. If I follow a clockwise loop around here, I'm going to add 12 volts across this battery. I'm going to add 6 volts across this battery. I'm going to lose IR for this resistor, and I'm going to lose IR for this resistor. Since there's two different resistors, I need to make sure I keep them identified, resistor 1 and resistor 2, in my loop rule statement. After I write it out, I can do some simplifying. 12 and 6 I can add together. I can factor out the i's. So this would be my overall statement for the loop rule. In the second example here, I've turned one of the batteries around. So when I'm following my clockwise loop, when I go across the first battery, we're gaining volts. This one is going to counteract that. We're going to be losing 6 volts across this battery. Then we're going to lose voltage across the first resistor and lose voltage across the second resistor. So my loop rule statement is 12 minus 6, because we're going backwards across the battery, minus IR minus IR. All right, again, I can combine the numbers and factor out the I to do a little simplification. So let's make a little note here. When you're going backwards, you lose voltage across the battery. My third example, a parallel circuit. The parallel circuit, we have 3 different currents. The current coming from the battery splits into 2 different currents and then adds up together again to make the current coming back to the battery. So we have I1, I2, and I3. We have 3 different loops here. So I'll go around the first loop. Going across this loop, going across the battery, I'm gaining 12 volts here. Going across the resistor, I'm losing I times R. Since we have different I's and different R's, we have to keep the numbers on them to keep them straight. So I have 12 volts I'm gaining, and I'm losing I2 times R1. And the sum of all of those has to be 0 in all of the loop rule cases. All right, the second loop I could do is around the outside of it. So following that loop, I'm gaining 12 volts here, and I'm losing IR across here. So this one is I3 and R2. Otherwise, the statement looks the same. All right, my third loop would be this one. And in this one, kind of interesting, here I'm losing the same IR, but this one, notice I'm going the opposite direction of the current. So when you're going opposite, I'm going to be gaining volts across this one. So I would write plus I2 R1, so I'm gaining volts across this resistor, and then minus I3 R2, I'm losing voltage across this resistor. Okay, so we'll make a little note on here. In the opposite direction, you gain voltage across a resistor. All right, let's look at an example. We have a bad car battery. This will be a circuit for your car. Remember, on the battery we have a EMF and an internal resistance between the 2 terminals. And the terminals, you have big fat wires hooking up to your battery, and they go straight to the starter. This makes a series circuit where we have 2 resistors and 1 EMF. So as the battery dies, not only is the EMF, the voltage, decreasing, but the internal resistance increases, which is also compounding your problem, because remember, the internal resistance uses some of the voltage that's provided by the EMF. So looking at our series circuit, I can find the net resistance is 0.25, And then I can find the current going through here. For the current, it's going to be the total volts divided by total resistance. Comes out to 40.4 amps. That's not enough to start your car. That's not enough to turn your engine. So we need to jump start your car. Someday in the near future, you're going to have car trouble and your battery is going to go bad. And you're going to remember your physics lesson. So pay attention. We're hooking the positive post to the positive post on the two batteries and the negative post to the negative post. So the good battery has a high EMF and it's going to provide a current which adds to your current, so we have a nice strong current to start your car with. To solve this, we're going to figure out what are these three currents. We have I1, I2, and I3. If you have three unknowns, you're going to need three equations to solve the problem. The first equation is going to come from the junction rule. Looking at this point, I have current I1 and current I2 going into the junction and current I3 going out. The junction rule says the sum of the currents entering equals the sum of the currents leaving. All right, the junction over here has the same equation. So normally we only use one junction when we're solving the problem. So the other two equations are going to come from the loop rules. So we have three different loops to choose from. There's a small loop on the bottom, there's a small loop on the top, and then there's the big loop around the outside. You need two loops, and it doesn't matter which two they are. Sometimes one of the loops is easier than some of the other ones, but you can't always tell by looking at it. So I'm going to choose this bottom loop first. Going around this loop, we have an EMF of 10.1 volts that I'm gaining here. I'm going to lose voltage across the starter, and I'm going to lose voltage across the internal resistance. And then I'm going to substitute V equals IR for each of my V's. So I'm gaining EMF, I'm losing IR for the starter, and losing IR for the internal resistance. And note that there's two different currents here, so I have to keep track of the currents with numbering. So I can put in the numbers for the resistors. Normally we skip these two first steps and we jump straight to this one. It's totally acceptable in this problem, and notice that we're not putting units in for the numbers. It just gets too confusing. So this is our statement for the loop rule for my bottom loop. And what I'm going to do is solve this for I2. Then I can divide through by the 0.1, and I have an equation for I2 in terms of I3. My second loop, I'm going to choose the outside loop here. So this time we're going to cross the good battery, so I had 12.5 volts. We're going to lose voltage across the jumper cable resistance here. I'm going to lose voltage across the starter. I'm going to lose voltage on the jumper cable on this side, and I'm going to lose voltage across the battery here. So we have a whole bunch of V's that I'm losing. I'm going to substitute V equals IR for each one. And notice for each one I have to carefully label what resistor and what current it is. You have to pay close attention to when you're labeling all of these. So I can do some simplification here. There's three of them that have current I1. I can factor those out. And then I'm going to solve this one for I1 in terms of I3. And then I'll plug in numbers they gave us for the resistance values and solve for that. So here I have the loop rule equation for I1 in terms of I3. Looking at the three equations we came up with, I solved this one for I2 so I can substitute it here, and I solved this one for I1 so I could substitute it here. That way I have all of them together in one equation, and there's only one unknown variable, I3. So I can simplify and solve, and I come up with 71 amps for current number 3. Now we can go back to this one. Remember, I solved each of these in terms of I3. So for the middle one, plugging in 71 amps in place of I3, I end up with negative 5.5 amps. And the bottom one, plugging in my 71 amps, I end up with 74 amps for current number 1. Looking at our final answers here, this negative current means that the current is actually going in the opposite direction. So this good current that's coming out of the battery is not only starting my car, but it's also going backwards through my battery, and that's charging my battery. So it's doing two things at once. It turns out we also hook up battery chargers and alternators in the same way to run current backwards through your battery, and that way it charges your battery. End of notes.